Okay, looks like we're ready to start. So the next speaker is Callum Reader from the University of Sheffield, who'll talk about measures and enriched categories.
Cheers. Thank you to everyone who made sure that this went ahead. Today I'm going to be talking about measures and enriched categories. And kind of the focus of this talk will be measures specifically on metric spaces. So a lot of work that's kind of gone into this categorifying measures on metric spaces has focused on something called the Kantorovich monad. And so this is a monad on the category of metric spaces, and it sends every metric space to a metric space containing probability measures on it. And we'll see later how this metric's defined. And so this is kind of first, I think, defined by Van Bruegel, but Paolo Perroni and Tobias Fritz have kind of given a nice co-limit construction of this. And what I want to talk about is, if we think about metric spaces as a type of enriched category, then we can kind of construct a similar monad by using double dual. And in a different context, this construction also gives rise to the ultrafilter monad. So what's the elementary approach to measures on metric spaces? So the idea is that a measure on a metric space X kind of gives volume or area or mass to its Borel subsets. So I think Swaraj mentioned this idea of a sigma algebra. Borel subsets are just the sigma algebra that's kind of generated by your metric. And again, as Swaraj says, a measure kind of, it will take in some set in the Borel set, and it spits out some non-negative real value, and it does so in such a way that kind of it follows some axioms which follow your intuition about sizes. So for example, if you've got disjoint sets, then the size of their union is just going to be the same as the sum of their sizes. And in particular, this is interesting for us because if you have some function from a metric space into the reals that kind of respects Borel sets both on the reals and your domain space, then it's called measurable. And what that means is that we can integrate it, because in some sense there is a volume or an area or a mass under the curve in the same way as kind of undergraduate calculus. And you define this by just taking limits of step functions in the same way as you would in undergraduate calculus. And all this kind of structure here, this works even if we use pseudometrics. So when I say pseudometric, in this case, I mean a metric space where sometimes your distances will be infinite. And that's kind of useful because it allows you to take disjoint unions.
Sorry, Callum, very confusing terminology. Because pseudometric usually means you can have distinct points at zero distance. And when you allow infinite distances, that's usually called an extended metric.
Yeah, so I think there's a lot of different terminology.
Those that I've never seen before.
Okay, yeah. So I think also sometimes pseudometric means you allow asymmetric distances. But okay, yeah. So I guess for the sake of this talk, we allow for infinite distances. And what's interesting about on a metric space is that sets of measures themselves have a pseudometric structure. So if you take the set of measures on a metric space, if you insist that they all have the same total mass, so the measures value on the whole space is the same. So for example, the set of probability measures, you get a pseudometric called Earth mover's distance. And kind of the intuition behind Earth mover's distance is it's sort of the least amount of effort to rearrange one measure into another. So if you're thinking about a measure as being a kind of a distribution of mass over some space, you're kind of moving that mass around in the most efficient way, and you're calculating how much kind of work you've done. So an example, if you start with a 3-point metric space, X, Y, and Z, then you've got a measure mu, which is generated by a half at X and a half at Y. So if we think of this as maybe 3 warehouses, we could say we've got half our goods at X and half our goods at Y. that's the kind of the current scenario, but we want to move to a new scenario where we've redistributed all of our goods evenly between the 3 points. And so what we could do is we could move everything to X and then redistribute from there, but that wouldn't be particularly efficient. And it turns out that the most efficient way to do this would be to move a sixth of our goods from X to Z and a sixth of our goods from Y to Z. And so you can see that then the Earth moves distance in this case is just a sixth times this fifth here and a sixth times this seven here. And in general, you get a formula for this, and this formula ranges over what are called short maps. So a short map is just a map between metric spaces such that it doesn't increase distance between points. So if you've got 2 points in your domain, then where they get sent to in the codomain will be they'll be at least as close. So this is kind of the elementary approach. So what's the categorical approach? Well, this relies on Lorbeer's idea of metric spaces as enriched categories. So in enriched category theory, you just take the definition of a category, but everywhere it says set and Cartesian cross products, you replace it with just some arbitrary V, and this V is going to be a monoidal category, and then you replace this Cartesian product with just some monoidal product, and in this case, we replace it with what we're calling R plus bar. So this is just the real line from 0 up to infinity, and we get a unique arrow from A to B if and only if A is greater than or equal to B. And the monoidal product on this is then just addition. So you can kind of see in the definition of a category, we have a set of morphisms between objects. Now we have some distance value, some non-negative real value between objects, where we used to have composition. Now if you just replace the arrow with Cartesian product, we just get the triangle inequality. So this really is a kind of distance. And where we used to have functors, we now have short maps. So essentially, an R plus bar category kind of has distances, but they can also be infinite and asymmetric. And as Prakash mentioned before, you can have a zero distance between distinct objects. So this is kind of a generalized metric space, but we're kind of more interested in involutive R categories. So an involutive category, sometimes called a dagger category, and the idea there is that you've got a contrary functor from your category to itself. That's the identity on objects, and it kind of what it does is it flips your arrows. But if you kind of take that data and translate it into this context, what it says is that your category has to have symmetric distances. So you can still have infinite distances, but they will be symmetric. And finally, this category R plus bar is closed, so it has internal harms, and these are just given by truncated subtraction. So 7 minus 3 is going to be 4, but obviously we don't have a minus 4, so 3 minus 7 just kind of stops at 0. So R plus bar is kind of enriched over itself by this truncated subtraction. So this is kind of how we think about metric spaces as categories, but then how do we think about measures? Well, this kind of follows from what's essentially a Riest representation theorem. So short maps are measurable, which means we can integrate them. So if we start with the set of short maps here on some pseudometric space, then if we have a measure, then we actually have a function which takes in a short map and it spits out some non-negative real value. And we'll see later that this is kind of uniquely defined. But of course, we said in the last slide that short maps are functors. And so in the same way that between functors, you normally have a set of natural transformations, you now have a natural transformation object in R plus bar. So it's kind of a natural transformation distance. And this is kind of computed as an end in the target category in R plus bar. And what it turns out to be is just some kind of submetric. So it's kind of like the usual submetric, but we don't have absolute values. Instead, we just have this truncated subtraction. And so it turns out that if your measure has total mass less than or equal to 1, then this F mu here is isn't just a function, but it's a functor. And so you get this embedding of, or this injection from the set of measures with mass less than 1, less than or equal to 1 on X, into this category of double Copery sheaves. So a Copery sheaf is just a functor from a category into its base for enrichment. And we're kind of doing that twice. So you can kind of already see how the double dualization comes in. But what's kind of interesting about this is that, of course, this category of double Copery sheaves has a natural transformation distance as well. And again, if you just kind of unpack the definition here, what you get is this supremum over these integrals. And if you recall, this Earth mover's distance from the start is formally very similar. And actually, they turn out to be identical. So if mu and mu have the same total mass, then these are identical. But if they have different masses, you can still define this natural transformation distance, and it will give you a generalization of Earth mover's distance. So there's a natural pre-order on measures, and this also encodes that. So if mu is less than u, in one direction your distance will be infinite, and in the other direction it will be 0. Okay, so if we're thinking of measures as a special kind of double Copery sheaf, which double Copery sheaves are measures? And to work that out, we need to think about what properties an integral should have. So if we're thinking of an integral as some here, what properties will it have to have? Well, firstly, it has to be kind of continuous with respect to analytic limits. So just limits of sequences, not categorical limits. So sequences of functions, pointwise sequences of functions. And it just turns out that all short maps are continuous. And so this is kind of easy to prove from the definition, but we're actually kind of working in an asymmetric case here. And kind of a nice way to get around doing the analysis is, so there's a result by Rutten which says that limits of sequences can be expressed as weighted colimits. And then a result by Bob Paré which says if W has a right adjoint, then any colimit weighted by it will be preserved by all functors. And so if you kind of tweak this result by Rutten, you can show that the weight for the colimit is going to have a right adjoint as a profunctor, and so it's just preserved by every functor. And so this is kind of a way to just avoid doing the category theory, avoid doing the analysis by just using these kind of abstract category theoretic results. And so the other thing that you want an integral to be is linear, but actually, if you've already got this continuity condition, it suffices to show that it's pointwise additive. So then you might say, well, if this is the domain, does this have a monoidal structure? Because we're thinking of this as a category. Does it have a monoidal structure given by pointwise addition? And this would work if your base for enrichment was Cartesian. So in the normal case, this works because limits are computed pointwise. But in our case, it doesn't work. So for example, if you just add the identity to itself on R plus bar, you get the doubling map, and this doubles distances, right? So it can't be short. And the reason this happens is that addition is not Cartesian, it's semi-Cartesian. So the unit in this case is terminal, but this isn't the Cartesian product. But there's kind of a workaround for this, and that's to think about partial monoids or par monoids. And the idea here is that this is kind of like a monoid, but it's not always defined. So for example, the unit interval 1 plus 1 is going to be, it's not going to exist because it doesn't land in this set, but a half plus a half, if you want. And where the addition does exist, it kind of follows the monoid axioms. And these things have what are called monoidal envelopes. So they're kind of the universal monoid that contains them. So in this case, what that will be is the non-negative reals with addition. And the idea is that what you do is you will take the free monoid on the unit interval, and then you just quotient out all the kind of pre-existing addition structure. And of course, you can kind of just define this in any monoidal category in the same way that you can define a monoid in a monoidal category. then you can define a par monoid in a modal category. So it's kind of the same idea, but instead of having morphisms here, you have partial morphisms. So it just spans where one leg is monic, and then composition is given by pullback. And it turns out that, so if you've got some base for enrichment V, if it's semi-Cartesian, then this co-appreciative category will have a par monoid structure. So if it's Cartesian, it's a monoid structure, but if it's semi-Cartesian, it's this par monoid structure. I mean, I say par monoid structure, I mean up to isomorphism. And it gives you a kind of a pointwise tensor. So this kind of inherits some of the tensor structure on V. And it turns out that measures with mass less than or equal to 1 are exactly par monoidal functors from your co-appreciative category into R plus bar. So they're just the things that kind of preserve pointwise addition. And the proof for this goes as follows. So if you start with some par monoidal functor here, then you can complete this category of short maps to the category of Liptz functions. Because this turns out to be the monoidal envelope. And so this par monoidal map now extends to a unique monoidal map. But the pointwise addition on Lipschitz functions can now be extended to its Cauchy completion. So if you Cauchy complete a category, the Cauchy completion will have will inherit a tensor via deconvolution. And so deconvolution measurables will give you pointwise addition. And then again, you get this unique monoidal extension. And this functor here turns out to be the integral for some measure. And so what you end up getting is that every par monoidal functor will give rise to some unique integration functor, unique integration function. But of course, if you've got an integration function here on the measurables, you can just restrict that to short maps, and that will preserve pointwise addition. So you get this kind of bijection. And so I guess just to finish by talking about monads, of course, we started this construction by looking at these double co-appreciatives. So mapping some category to its category co-appreciatives on co-appreciatives. And so this immediately kind of comes equipped with some double dualization structure. But actually there's now a subfunctor taking you to par monoidal double co-appreciatives, the category par monoidal double co-appreciatives, and this kind of inherits the same monad structure. And so for some arbitrary V, on VCAT you have this par monoidal monad. And kind of in examples, these examples aren't particularly enlightening, but if we look at R plus bar, this gives you kind of some kind of generalized metric space. And if you plug in a normal metric space, you'll get measures less than or equal to 1 with Earth movers distance. If we enrich over true and false, you get preorders. And on these preorders, you get a monad which gives you filters on the upwards closed sets. And like I said, that's not particularly enlightening. But you can instead look at involutive categories and look at the maximal submonad of this monad. And in this case, if you enrich over R plus bar, again, we get things equivalent to pseudo metric spaces or metric spaces with infinite distances. And what you get is something it's not quite the Cantor-rich monad because it includes all probability measures, but it's very similar to the Cantor-rich monad, and kind of the unit and the location behave in the same way. And as I mentioned before, this is kind of the same as, in some sense, as the Giri monad. And in the case of preorders, if you look at involutive preorders, what you get is sets. And if you look at the maximal submonad in this case, you get the ultrafilter monad. So this kind of follows on from, I guess, from work by Tom Avery and Tom Leinster, and show kind of the Giri monad and the ultrafilter monad are both co-density constructions. So yeah, the punchline here is that this monad structure and this kind of structure of Earth movers distance just kind of falls out in some way from the enriched category theory. So I guess that's me finished. Questions?
Thank you. So questions, anyone?
I have a question if I can ask.
Yeah, go ahead.
Yeah.
So yeah, thanks for the talk. It's very nice. So could you please go back to the last table that you've shown?
Yeah.
So I see there's a monad of measures lesser or equal than 1 for the R bar plus case. So
Yeah.
I suppose we could view that as a generalization of the Kantorovich monad to general Levere metric spaces, right?
Yeah. So in some ways, I think part of the problem is it kind of behaves quite weirdly for asymmetric metric spaces. So if you don't have this kind of pseudo metric structure instead, you don't really get measures on the asymmetric. You just kind of get something a bit weird. And so if you try and do this thing with the proof before, in some way, if you try and do it on it, so if you've got an asymmetric metric space, you've got two topologies, right? Because you've got open balls where you look at distance to the point and open balls where you look at distance away from the point. But if you try and kind of do this for these asymmetric metric spaces, it sort of can't work out which topology to use. I've kind of probably not expressed that very well, but
what if you use like this adjunction between subsets and enriched presheaves, whose score is usually given by the closed sets? Doesn't that give you a topology?
I don't know.
Okay, no, I don't know.
Could you explain that a bit more?
I mean, maybe let's do this offline, because
yeah, sure.
But definitely, if we want to talk about this thing, I've found all of this actually extremely interesting.
Cool. Yeah, that'd be good.
Yes, David Jazz, go ahead. People cannot unmute themselves.
Hi, thank you. Can everyone hear me? Okay. Hi, thanks. This is a wonderful talk. This was really interesting. I'm wondering about the relationship between parmonoidal structure and promonoidal structure. Not just because they sound so.
Yeah, so this is something I was pulling my hair out over. I really thought that this would be a promonoidal structure, and I spent ages trying to show that it was. And every time I showed that I had a promonoidal structure, it kind of reduced to a weird monoidal structure. But so yeah, it is kind of. So I'm guessing that you were kind of thinking that maybe, obviously partial functions are a special kind of relation. So you think of a partial morphism in categories would be a special kind of pro-pointer. But actually, then like partial morphisms in VCAT are kind of the wrong notion of a partial functor. So Bob Parry's got a paper on what he calls Mealy morphisms. And Mealy morphisms seem to be, at least with respect to profunctors, they're kind of the right notion of partial functors. So I mean, in some ways, this parmonoidal thing is a bit of a hack because it doesn't seem to fit nicely with functor structure.
Thank you.
Okay, well, let me thank you once again. That was a great talk. Very interesting to see the enriched category theory point of view coming to play.